Welcome back to the channel. Today's lecture is going to be focused on the primary Earth processes that shape our planet and affect life. It's one of the focused areas for the AP exam, and remember, we need to only really cover units 1 through 7, and this is an area that we kind of glossed over earlier in the year, so I want to go back and make sure that we really nail this down and you understand these processes, because I predict there will be many questions about this coming up on the AP exam. So let's get right to it. So as the slide title indicated, the first process we're going to address is plate tectonics and composition of the Earth. So let's go ahead and begin to look at some of the PowerPoint. So as we look at the graphic displayed, you'll see the 4 layers of the Earth notated: the crust, the mantle, the outer core, and the inner core. As far as composition goes, it's very simple to remember. All you have to remember is solid, liquid, liquid, solid. There's also a very big size disparity between these layers. You'll notice the crust is very, very thin compared to the mantle. You'll also see that the continental crust is much thicker and much more buoyant, actually, than the continental crust, which is extremely thin. There's also the functional layers of the lithosphere, which is rock, the asthenosphere, which we're going to talk about shortly, and then the mesosphere and core. So this graphic shows the boundaries that exist between the continental and the oceanic crust, actually driven like a conveyor belt by the asthenosphere. Remember, the asthenosphere is that border between the crust and the mantle, where heat is circulating from the mantle, actually coming up from the core of radioactive materials. The heat rises. As the heat rises, it's going to basically push its way up, and with that upward motion of material and heat, it's actually going to push the lithosphere in opposite directions. As that convection cell continues to rotate, as it passes along the lithosphere, that heat begins to dissipate. You begin to cool, which increases density, and as it begins to sink, you're going to have a pull motion, also aided by gravity. A trench is created there. Where you have the ridge push, you have mountains being built. So this process is repeated all over the planet with a building of mountains and volcanoes and the creation of trenches. So when you're thinking about what is being moved around by the asthenosphere, think of the crust much like an eggshell. You gently squeeze a hard-boiled egg and it breaks into many smaller pieces. Now, those pieces, depending on whether they are continental crust or oceanic crust, as they are moved about, will collide, or they will be pulled apart, or they will slide past one another. On the next image I'm going to show you, you can kind of see these boundaries in between these plates as outlined by the red. So in this image, you can actually see the different plate boundaries, and you can discern the ring of fire there along the Pacific Plate, the west coast of California, extending down through South America, and then going all the way up to Alaska, going across the Bering Strait, and then repeating the path along the coast of Japan, down through Southeast Asia, and then before turning back towards the east across the Pacific Ocean. So based upon the type of plate, whether it being oceanic or continental, will determine what is actually occurring at that plate boundary. If you're looking up at the northwest coast of the North American continent, that is all a subduction zone, where the Pacific Ocean is actually being forced under the North American continent as it moves slowly to the west. The plate boundaries and the movement are all characterized by the collision that's occurring or the divergence that is occurring. As you can see on this graphic, you have convergence zones where you have oceanic crust being pushed under the continental crust, and you can see that on both sides of this image you have the creation of volcanoes. At the same time, there in the center of the image, you see where the crust is pulling apart, and the asthenosphere is actually forcing its way upward. That would be the creation of a mountain chain or a mid-Atlantic ridge. That is a divergent boundary. At the same time, you also have one other type of boundary, which would be a transform boundary or a sliding motion as opposed to moving apart or actually colliding. So let's take a closer look at these plate boundaries. We'll start with the convergence zone. As you can see in the upper left-hand corner, you have an ocean-to-ocean collision. Even in that case, you will still have one of the plates will be forced under the other, and you can see that there is an island chain or an island arc that is being created there. That is not necessarily a hot spot. That's a little bit different. This is an actual collision between two oceanic crusts. Right next to that is oceanic and continental. Strongest earthquakes. This is where you have a great subduction, the oceanic crust being forced under the continent, and always you will have a volcanic arc, mountain chains, and volcanoes, active volcanoes, that would be occurring there due to the fact that oceanic crust is diving down. It is melting as it enters the asthenosphere. It has water in it, which is going to force it upward. The next at the bottom, you'll see that you have a continent-to-continent collision. Not any creation of volcanoes here, but this would be evidenced by something like the Himalaya mountain chain, where the subcontinent of India is crashing into the continent of Asia, making the largest mountains in the world. So a hotspot is a little bit different. This would be like the Hawaiian island chain. Hotspot is actually a very narrow place in the oceanic crust where you have a hot plume that is rising up from the mantle. And as the oceanic crust moves, the plume does not. And so you will have a crescent-shaped arc of islands that are created. Look at a map, look at Hawaii. The newest ones are the smallest ones, and you can actually see the crescent shape forming because as the Pacific plate passes over that hot spot, material is pushed through the crust and mountains are formed, in this case, volcanoes. Next, we'll take a look at a divergent boundary or a spreading center, as well as a transform boundary, which is where you have the sliding motion. With a spreading center, again, that would be where the crust is actually pulling apart. This would be primarily in the ocean, in the middle of each of the oceans. It also occurs in the Great Rift Valley of Africa, where the continent is actually being pulled apart at that location. Um, you have an upwelling then of molten material coming up from the asthenosphere. Again, not necessarily volcanoes, but you will have a mountain ridge that is created. And then each succession of that is going to push new oceanic crust, again, towards the continents to have further and further collisions. You'll also see the transform boundary. We should be very familiar with this. This is the San Andreas Fault here in California. We don't have to worry about it colliding. What it does is it slides. One side of the North American plate is moving to the west and to the south, while the other small little piece of the plate that is stuck between the Pacific plate and the North American plate is moving to the is being pushed actually to the north and west. Eventually, over the next course of 1,000,000 years, Los Angeles and San Francisco will become closer and closer together. Eventually, you'll be able to walk. Give it enough time, and the city of Los Angeles will actually be in the Bay of Alaska. Now, something to make sure we keep in mind, regardless of the motion, divergent, convergent, or transform, earthquakes are going to be created from that movement. We measure those earthquakes and the size and strength of the seismic waves that are broadcast when you have that sudden snap, that sudden release of tension that vibrates throughout every rock layer. In fact, it will ring the earth like a bell through the mantle. Um, we have two terms that we use to describe an earthquake. The focus is actually the point in the earth, usually very deep in the earth, where the earthquake actually happens, where the release occurs. The epicenter, which is what we're familiar with, is the location on the surface. Um, Meaning the proximity to a town or a location. This isn't necessarily deep into the earth when we talk about the epicenter. The epicenter is directly above where the focus lies on the surface. Now we measure the earthquake, or actually it generates two types of waves, a P wave or a primary wave and a secondary wave or surface wave, an S wave. The damage is not in the P wave. The P wave travels very quickly, immediately extending in all directions from the focus of the earthquake. The surface wave or the S wave travels much slower, but that is where the actual shaking occurs. And so the P wave is generated instantly. That's how we can determine there's an earthquake that has happened, and we can use seismometers to determine the location through triangulation. But the P wave, again, is the primary wave. The S wave, the secondary wave, the surface wave, that is where you actually have the shaking, the waves, the back and forth, the up and down motion that causes so much damage. Again, the biggest earthquakes are in the subduction zones where you have the oceanic to continental collision. In fact, the biggest earthquake in the world occurred off of the coast of Chile in South America, a 9.6. Chile actually holds the record for two of the top four earthquakes in the world, a 9.6 and a 9.2. Now, I briefly mentioned the seismograph. Now, we use a scale called the Richter scale. It was invented by Charles Richter, his wonderful face right there. The way that it works, though, is you have a magnitude 1 earthquake, and magnitude 2 earthquake is 10 times the strength of a 1. A magnitude 3 is 10 times the strength of a 2. 100 times the strength of a 1. A magnitude 4 then becomes 10 times stronger than a 3, 100 times stronger than a 2, 1,000 times stronger than a 1. So you can see what kind of energy is going to be released when you get up into the 7s and 8s and the 9s, which are complete devastation. Fortunately, the San Andreas Fault, not capable of anything no 9.0 or greater, probably not even something in the 8 range. But a 6.5 would be very devastating. That would still be an immense amount of energy that would be released. Okay, so we talked about that every motion of the Earth, of these plates, as they're being pushed around by the asthenosphere, colliding, moving apart, sliding past one another, they're all causing earthquakes. In this next graphic, I want you to pay close attention to the arrangement of these earthquakes, and you can, by looking at that, especially the magnitude, as well as the sheer number, the sheer percentage of all of the earthquakes across the planet, where they are all clustered, you can really easily identify what kind of plate boundary you're actually looking at. So as we look at this graphic, you'll notice that the date, August 20th through October 2nd, 2006, notice the clustering, the grouping of these earthquakes throughout just this short period of time. Notice the depth of where the earthquake is occurring, again, the actual focus. And then also look at the magnitude and the amount of damage that you're seeing there. That's the Ring of Fire in all of its glorious wonder. The major subduction zone, the site of the largest earthquakes in the world. So following right along with earthquakes and the movement of the Earth through those collisions and convergence zones and subduction, you have the creation of volcanoes. And if you look at this graphic, you'll notice that Boy, surprise, surprise, they are clustered in the same locations as those big earthquakes that we looked at. Now, there are only three types of regular volcanoes that we're going to be looking at. A shield volcano, which would be like the Hawaiian Islands. Cinder cones, those are small volcanoes, just like they sound, made out of small debris, and they make the classic volcano shape. And then you have the big boys, the stratovolcanoes or composite volcanoes. These are the ones that are explosive, and when they go, they cause lots of damage. And again, most of those are going to be found along the Ring of Fire. Caldera, a famous one, would be Yosemite, or I'm sorry, Yellowstone. The most famous caldera of all, a collapsed composite volcano. Now, in the terms of Yellowstone, you're talking about a super volcano. This is not the same as a composite or a stratovolcano. Yellowstone is its own bird. There are only 7 of these in the world, and we probably here in the United States have the most dangerous one of all. Over the last approximately 3 million years, Yellowstone has erupted about every 650,000 years. Um, the last eruption has not occurred for over 750,000. Does that mean that Yellowstone is overdue for an eruption? No, it's not that kind of a timetable. Yellowstone will warn us when it is about to go. We will see signs of upwelling. We will see signs of increased seismic activity as more and more magma is reaching farther and farther up into the crust. Now, Yellowstone has shown us signs of uplift in the past. Does that mean that it is again due for an eruption? No. We cannot make those predictions, just like we can't predict when an earthquake will happen. We can only see the signs of something to come. There's no way for us to actually put a date on when Yellowstone will erupt. Will Yellowstone erupt? Absolutely. It's done it in the past. It will do it again in the future. And when it does erupt, it will change the landscape of North America. In fact, it will affect the entire planet with the amount of discharge, the amount of sulfur dioxide that will be expelled into the atmosphere, the amount of ash and dust. It will cause what we call a nuclear winter and could, in most cases, cause an ice age that would take maybe a couple hundred years to come out of. Well, that should wrap up the composition of the Earth as well as a brief overview of plate tectonics and why we have earthquakes and why we have volcanoes and why we have the landscape features that we do and why we have the Hawaiian Islands in the center of the Pacific Ocean sitting on top of a hotspot. If you have any questions about any of the content here, you can always place a question in the comments area. And hopefully, this helps you out a lot. And this was, again, the first of many of these miniature lectures that you will be able to access through this channel. Again, as always, stay safe and wash your hands.